All right, now we're going to briefly contrast how these different models performed. We're going to be using the metric mean absolute error, so i.e. the count of people our model over or underestimated by. This is one of the simplest varieties. There's a lot of other approaches that we could take, but we're going to talk about those in class later. So the first thing we'll want to do is create a new data frame, and this new data frame is going to hold the information on how well the different models did. So we'll create MAE and historic. So this is going to be the current model that we're looking at, and then when I say historic, I mean based on September 1st and September 2nd, because eventually we're going to be using these models to predict to September 3rd. So let's go ahead and create our data frame. All right, and all that does is create a completely empty data frame. So, accuracy data frame is going to have absolutely nothing in it except for the names. And so now we're going to want to add all of those different model types to see how well, they did relative to one another. What we want to do here is we're just going to pick one of these to do our prediction. So let's do from sklearn.metrics. All right, so what we're doing here is we are taking our metrics. So there's, again, many different accuracy metrics. We're choosing the mean absolute error, and we're going to calculate just for lasso the mean absolute error, comparing the true y, so this is the true number of people, to what our model predict. Now, this is strictly internal accuracy, right? So we will engage with external accuracy programmatically later on in the course, but for now, we are just judging these based on the internal accuracy. So when I run this, we'll see the lasso MAE. And there we go. So on average, across all minutes, we are estimating incorrectly by about 42 people if we were to use lasso. So the question is, which one of these is the best? Which one of our models is the best? Let's save this into our data frame. So we'll do the accuracy. All right, there we go. So we're going to append to our accuracy data frame this value. So I'm going to run this. When we run this, I'm just going to take a look at accuracy data frame, and now we have one model, lasso, and that MAE, the 42. So we're going to repeat that for every single one of our models. Now, I'm going to cooking show this because I've already done it. And so we'll have all of those in one giant data frame. So the exact same thing over and over again for every model that we just went through. So we'll run this, and we can take a quick look at our accuracy data frame. So now we have everything. And because, we can, let's do a quick visualization to see which one of these performed the best. So we'll do a bar plot with our MAE historic on our x-axis and the y being the model type. All right, and just like that, we have a beautiful visualization that very quickly shows us that in terms of the mean absolute error, our radius regressor was actually the best. Finally, we're going to take the best performing model, the radius model, and we're going to apply it to this near real-time data stream. So this is the first time you'll be applying a model in real time. So first, let's do matplotlib inline. Notebook, because we're going to be using a dynamic plot. So this allows us to create plots that are dynamic as opposed to static. So everything we've been doing before this has been static, and now we're going to actually be able to interact with our plots. We're going to import a few things. So we're going to need matplotlib. All right. So just to walk through here, matplotlib will let us make their visualizations. Time allows us to do some manipulations with our timestamps. And this is very important. This request.packages URL lib disable warnings. The reason we put this is you'll remember all the way back at the very beginning of this lab, we got this warning. So when we went to download this data, we actually had this verify equals false. We don't care about this warning. We already know that our connection is secure because we're going to a William & Mary server and there are rules for that. And we don't want every single time we ping the server, because we're going to ping the server every minute. We don't want every minute this warning to come up. So we're preventing that warning from popping up by putting in this request packages URL lib3 disable warning. The first thing that we want to do is we want to set a start time for our algorithm. So we'll go ahead and start on the 1st of September. So we're gonna look at 2 days of our algorithm. That's just how well our algorithm, the internal accuracy, how well did our algorithm do when we're comparing to the current data. So we'll set current time, and we'll create a timestamp. So this is saying we're going to pretend like it is the September 1st of 2019 at midnight. We now need to create a data frame of what we want to visualize each minute. So again, we're going to be looping through creating kind of hypothetical minutes, and we want to save some information every minute to kind of plot out to see how well our algorithm's been. So every single minute, let's go ahead and save the timestamp. So we want to know, when our measurements occurred. The true person count. So this is going to be what the algorithm actually told us the number of individuals in front of the camera were. The estimated person count, and this is going to be our algorithm. So this is the radius, the radius model. So this is going to be how many people our radius model predicts, and then the MAE. So every single minute, we're going to save all 4 of these bits of information. Let's go ahead and create our data frame that we're going to use to save that. All right. Now we have to do a few kind of tricky things to get the figure to kind of draw how we would want. So first we have to initialize the figure. So we're going to do fig equals plt.gcf. So we're telling Jupyter create a empty figure. And you'll see here Jupyter has obliged by creating an empty figure. Nothing's there, it's just, figure. Let's tell it how big to make it. You may have to adjust this depending on your own computer monitor. And then let's tell it to actually show that figure. So there's, again, we have our empty figure, and now we're actually showing that figure. So you'll see figure 1, there's absolutely nothing there. Fig.canvas.draw. So this is not going to do anything right now. This is just going to allow us to refresh every single minute of our script later on. And then legend draw equals 0. So right now, we haven't drawn the legend. We only want to draw the legend the first minute, because otherwise every single minute we would redraw our legend over and over and over again. So this will prevent that from happening. All right. Now what we actually want to do is we want to create a loop where we're going to loop over every single minute. So while current time is less than or equal to, or less than pd.timestamp 9/3/2019, 23:59. So what we're saying is we're going to do everything in this loop as long as current time, which you'll remember, it's starting on September 1st at midnight, as long as current time is less than the 3rd at 23:59. So we're going to go through every single time step here. What we're going to do every single minute is we're going to request the data from our web server. All right, so this will look very, very similar to what we did before, but there's a couple of key things that have changed here. The first thing is timestamp start is now a string that we can change every loop of the while. So, we're going to go through with our first current time, and we're going to put in this. The end and the start, in this case, are both going to be equal to that current time. So we're going to have that kind of the range that we're going to pick is going to be that current. We're just trying to get the 1 minute. This is the equivalent of how most real camera systems work, is every minute you get the most recent set of observations. Cameras and other kind of edge sensors generally don't have big hard drives on them. They can store stuff that happened over the last minute, but not beyond that. So we're going to replicate that with this particular API call. We're going to pretend that every minute, all we get is what happened in the most recent minute from the camera. And that's what's going to be returned here. Then, same as before, we have our headers, right? So there's nothing here. So we're going to ask for 1 minute at a time. So every single loop, R is going to contain information from 1 minute. Let's go ahead and do the same reading that we did before. So we're going to go to our next thing. We're going to do the DTA. So this is going to be the exact same thing we did before. We're going to read the response. And then just like we did before, I'm going to calculate the minute that we're in as well. So just to illustrate this, I'm going to go outside of the while loop, and let's actually print DTA. Well, actually, before we do that, we're going to add in the incrementer. So this is going to be where we actually go in and we add current time. So let's do, just for the sake of example, let's do current time equals current time plus PD time delta minutes. Let's do 240. So we're going to get very few rows of data because we're only going to ping the server for every 240 minutes of data. So let's run this. There we go. And so we're starting to get the data back from the server. So this was the first minute, the 0th minute. Then we got the 240th minute, just as we request. So we should get the 480th, 720th, 960, so on and so forth. So every 240 minutes of information, every time this while loop goes, we get the next minute of information where we're skipping, right? So we're only doing every 240. So we want to take this information and use it to create our own estimates and then kind of visualize that in a meaningful way. So first and foremost, let's actually go in and let's find out for our current iterations. We have our minutes here. We've created our minutes from that particular time step. Let's now go in and create what that timestamp is. So if we look at the response, right? So for this particular response, you'll see this is the response for a given minute. We have the value timestamp, which is this pandas timestamp. So DTA timestamp, we're just saving this as the variable timestamp. So we actually have that in memory for this iteration. The next thing we want to do is we want to save the true number of people that the camera saw, which you'll recall is person count right here. So for the first minute, this is at midnight, there are 0 people that it saw. So we'll have true person count is equal to person count. The next thing we want to do is we actually want to clean this particular data frame. So just like we've done before, literally the same. We're going to go in and we're going to drop those columns that we're not using. So PD times, timestamp, male count, female count, approach count. This is the same thing we did before. So nothing has changed. We are also going to scale our X variable. So if we go down here, we'll have scaled X. Remember when we were so up here, when we created our example case, so if we go all the way back to our scaling, we had this X example where we're scaling only one row of data. That's the same thing we're going to be doing here. We're just going to be scaling one row of data because the camera is only giving us one row of data at a time. So scaled X here, this is going to be the scaled values for X of that one row. With this scaled, we can create our estimate. So our estimated person count is going to equal the rad neighbors, because this is what we're going to use in this. This was our best performing model, scaled X. So this prediction will give us the overall prediction for this particular row of data. And then the number of people, the actual estimate, is stored in 0. So if you look at radneighbors.predict scaled X, and we can do this real quickly. So we'll scroll down here, just take a look. Oops. Pick one example. We'll take our X example. So if we now look at this estimated person count, 56.8, right? So we're just saving the actual estimate for that one row. That's the purpose of this radneighbors predict X example. If we take off the 0 and we do the same thing, we get this array, right? And we don't want the array, we want the actual float estimate itself. All right, so let's get rid of this print. And so what we're going to be doing now is we actually are going to go through, and for every single one of these iterations, we're going to have the estimate for the current timestamp. So if we print estimated person count, what we'll see here is every single iteration, the number of people that we are predicting the camera saw. So this will go through the entire record for every single minute of data that we request. This is cool, but it doesn't really give us a lot of actionable information. It's not a very clean way to look at the data. So we do want to do a little bit better here. The first thing we're going to do, and I'll delete this print. So the first thing we're going to do, let's calculate our mean absolute error for every single minute. So we'll do the true person count minus the estimated. So this is just the absolute value difference between these two. So we're calculating MAE. And let's save. You'll remember we created this data frame up here that we want to save our information in. Because again, every loop of this while loop, we're only getting 1 minute. So we want to save all of the minutes that came before. And we're going to save the timestamp, the true person count, our estimate, and our error. So we'll go ahead and do that here. So pred df. Good. So we'll go ahead and run this. And again, we still have no figure. As soon as this is done, so we'll wait just a moment. And remember, we're not printing anything out now. So we're waiting for the API to respond. Okay, so now we're done. Let's take a look at preddf. All right, so preddf now has gone through, and you'll remember we had this set to 240, so we're only pinging the server for every 240 minutes, and we're getting these estimates. So this means minute at 2019, the 3rd at 8 o'clock, we are predicting 44 people. There were truly 54. So we have an error of 9. So we can see what this looks like over time. But now we actually want to do better. In practice, these types of algorithms, because they're online, would be constantly getting new data in every single minute. And so we would want, a loop that would allow us to do that. So let's actually create something that visualizes this over time. So we're going to create a plot. So plt.plot. And the first thing we have to do is set our x values to the timestamp, because the x of our plot is going to be the timestamp values. The next thing is the true number of people. This is a line type. So this tells it to make a green line with I believe it's actually green characters in this case, so it will give us little green markers. And then we need to label it. Now, if we run this, we'll do one more thing. Xticks rotation equals 90. So this will just make it look a little bit nicer. So if we run this, and we'll go ahead and run this, what we'll see is a plot will start to actually come out here. Oh, sorry, one more issue. We also need to add in fig.canvas.draw. Okay, so this will actually redraw it every single iteration. So here we can see, we'll start to see over time these green dots. So the times are on the x-axis, and the green dots, we're going to get about 19 of these because we're only getting every 240 minutes. But the green dots are the true number of people that we observe, the true person count in this particular case. And it's already done because we are skipping so many minutes. So you can see that pattern. We now want to compare this true number of persons to our estimates. So let's go ahead and add another plot. So we'll do plt.plot. And you can start to see our estimates in blue versus the truth in green. So the difference between these two each time step gives you an idea of how much error there is. And then finally, we'll go ahead and add in all right, so you'll see a couple of new things. First, I added the mean absolute error. So I'm just adding a new line. This means a red dashed line. If you look up the matplotlib documentation, there's all sorts of different little commands you can put for different colors and shapes of lines. And then I added here, if legend draw equals 0. So you'll remember, initially, legend draw is equal to 0. So the first time this while loop happens, this will be true. We'll plot the legend, and then we'll set legend draw equal to 1. So this will never be true again. So we're just going to create the legend one time. And then type.layout just makes it look a little bit nicer. So we'll go ahead and run this, and this should be our final set of code that will actually do our near real-time predictions, again, every 240 minutes. So we'll run this just as a test. And there we go. So you can see a rough trend of the MAEs tending to increase over time, which makes sense, right? Up until the end of the second, this is all of the data that we used to fit our model with. And then once you get to September 3rd, this is the data that we didn't fit our model with. And so the error does tend to increase a little bit. But now finally, and I'll leave you guys on this with a beautiful musical outro, we can actually set this to be any time step we want. So we can set it ultimately to be 1 minute or 30 minutes or whatever we would like, and we can see the full model, how it would look if every single minute, for example, we were actually receiving additional data.